Okay, maybe you can start now. Okay.
Okay, sir. Okay. Good afternoon, everyone. So today I will talk about the theory of Floquet and its stroboscopic and non-stroboscopic dynamics, and how the dynamics are gauge equivalent to each other. And then I will try to give some perturbative methods like the Magnus expansion or effective theory, where we can approximate the Floquet Hamiltonian in the high frequency regime. So the Floquet theory is actually first came in mathematics to get the solution of the periodic linear differential equation x dot equals to at into x, where at is a periodic function. In the context of physics, we will apply this theory for the Hamiltonian when the Hamiltonian is periodic in nature. Especially this kind of problem first came in the context of classical mechanics, where we actually studied the stability problem of the periodic orbits like things. And for the quantum case, the linearity of the Schrodinger equation was guaranteed from the very first when it was developed. And there we can use this kind of Floquet theorem. So first I will start from the time-dependent Schrodinger equation, which is I into ddt of psi t equals to ht into psi t. And here the whole dynamics of the psi t, this is illustrated by the unitary evolution operator u t2 t1. And if I want to find the wave function at a later time t2, it will be by the unitary operation of the evolution operator. Okay, so but for a time dependent Hamiltonian, how we can write the structure of this unitary evolution? We can write it as the exponential of minus I ht dt. Here this time ordering part is very much important because ht is not same at each and every time, and this is unitary evolution, and this shows that if the Hamiltonian is periodic in time, so the evolution operator is also invariant under discrete time translations. Like if we translate the time in this regime, then where this n is integer, then we can see that this should be same. The Hamiltonian is periodic in time. And for this case, we can write the evolution operator for a time period. This is same as multiplied by one time period to the power n. Okay. Now, so we can define this evolution of a single period.
Ivan, how did you get to this relation? Can you explicitly? So you are trying to say that if my Hamiltonian is time dependent, let's say I can always define my Schrodinger equation, I can define unitary operator, right?
Yes, yes.
This way. So irrespective of h is time dependent or time independent. If h is explicit, h has explicit time dependence, then you have this time ordering and right?
Yes, yes, yes.
If it h is not explicit time dependent, then you have you can immediately integrate this out, right?
Yeah, yeah.
No, I didn't get like once you have ht, which is a periodic, like it has explicit time dependence, and it is periodic in nature. The full Hamiltonian is periodic in nature. how did you get to this relation? Like you. So can you explicitly show how you are going to get to this? Let's say ht equals to ht plus tau.
Okay. So suppose if I have a time evolution like this, I can write this evolution as okay. So if we just that means that this equals to
No, the last. Okay, yes.
and each and everything.
Ivan,
Yes.
so are you saying that this breaking can be done in period of capital T only?
Yes. Just
not
in one time period, the Hamiltonian will be same evolution. That's why.
So that is why you can break it in this.
Yeah.
Okay. And if there is some arbitrary T prime, that will not be like this.
Yeah, you can break it, but the expression, the value of the each expression will not be same.
Acha. But I can break it.
Yeah. You can break it every time.
Okay. So, but the time dependency of the Hamiltonian will not affect.
The time dependency. Yes. See this expression. What the evolution operator. I have written the full things in time ordered form, na?
Time ordered form. Then.
Yeah. So this integration T1 to T2, see the Hamiltonian is varying. Suppose I am thinking the Hamiltonian is constant for T1 to T1 plus del T1. Okay. So for this you write the first evolution, then the second evolution, then the third evolution. Okay.
Yes.
Yeah.
Yes.
You can split it in multiplication form.
Okay. Yeah. Okay.
Yeah.
No, actually, yeah, probably Ritika was trying to understand. Let's say in general, if my Hamiltonian is explicit time dependent, then and if it's not periodic, let's say I don't know whether it's periodic and a priori I don't know. Okay, then in general you can divide by any time, right? In
yes. Just if I notice only this expression.
Yeah, I can do it irrespective of now. If it is time periodic, the Hamiltonian is, then only this helps. This dividing in terms of this capital T time period. The capital T is the periodicity, right?
Yes.
That would help you to solve the problem, probably.
Yeah.
Okay.
So as at each and every time period, this is equivalent to 1. 1 means this. So you can write that u t naught plus t naught in place of the each element. And so totally we are multiplying it to the power n. Okay.
So once I have, let's say I have a time periodic Hamiltonian, and that means your unitary operator is also periodic.
If the Hamiltonian is time periodic, then the evolution operators would be periodic.
Okay.
So the Floquet theorem says that if the Hamiltonian is time periodic in nature, then we can write the evolution operator T naught plus T naught in an effective form, which is this. And this HF is just an effective Hamiltonian. and which maintains the unitary property of the unitary operator. Okay, this is the theorem by Floquet. And one thing I want to mention that in maximum case, this HF is dependent on some time t0. Suppose I have a Hamiltonian, I am giving a drive, and the Hamiltonian is moving along this. Suppose I am starting from t0. Okay, then I am starting here. If I want to see this dynamics, the Hamiltonian will be dependent on this.
I mean, does it mean that it depends on the initial condition?
Yeah. This is kind of gauge.
Okay.
Okay. Also, as this is unitary in nature, so this HF T0 is always Hermitian in nature. So now come to a general evolution.
So Ivan,
Yes.
one clarification is like
Yes.
you said that depends on H effective of T0.
Yeah,
So
yeah.
if I want to write at T0 T N T.
Yeah.
That will depend on T0 plus N minus 1 into T. But as it is periodic in T, that is why you are doing this. That is the reason why you write.
Can you repeat the question again?
Like if my like where you written the capital T, if there is NT and
Yes,
where
yes.
there is only T0, if there is T0 plus N minus 1 into capital T.
Yeah. That will be fine. Same
then
as the HF T0.
Then my HF will be dependent on T0 plus N minus 1 into capital T, right?
Yeah, but that is effectively again HF T0.
Yeah. Okay, that is the reason you can write it as
Yes.
form. Okay.
Yes.
Yeah.
Okay, now see general evolution.
So even is there any other property of this unitary operator? Let's say once you write this U T0 plus T, so you are saying according to Floquet theorem,
Yes.
if the Hamiltonian is time dependent, you can irrespective of the if just any Hamiltonian is time periodic, you can write unitary operator by some effective Hamiltonian HF times T, which is the periodicity. Is there any other? And you are saying HF may depends on the initial starting of your drive, right?
Yes.
Then it has the hermicity.
Yes.
Do you know any other properties of HF? These are the only properties, or you have any other constraint of HF or?
That
Okay, let me ask you, how do you calculate HF? If you know the unitary, so you are saying you know the unitary operator, right?
Yes.
From your Hamiltonian.
Yes.
Right? As you wrote, HF e to the
Yeah.
HST. So you need to compare the both sides to get HF.
That will be minus I 1 by IT into Ln of U T0 plus
I
T.
see. So once you know the unitary operator, then you can calculate HF, whatever the order, right? So okay. I just wanted to know that this expression how to calculate HF. So HF has this form.
Yes.
Generic form, right?
Yes.
It's not any high frequency, low frequency.
No. This is general. Okay. Now I want to talk about the general evolution. I am starting from T1 and going to T2. So first I am going to T1 to T0. Then I am going from T0 to T naught plus NT, and then from T naught plus NT, I am going to T2. So we can write it as, see, this T naught T1 is smaller than the time period. That's why I have broken this in this kind of forms. Okay.
Ivan,
Yeah.
can you show the expression of HF? This is
Yeah,
minus 1 over IT, right?
Yeah.
And HF must be Hermitian, right?
Yes.
So the second term will be also, because there is a minus 1 over IT. If you take the complex conjugate,
Yeah.
that will not be Hermitian, right? Hello?
Yeah. Probably, see, in this U, you don't know the expression of U. This is itself.
So you are saying that must be some
Yeah.
complex.
Here something is written, na?
Yes, that you will take care of its hermicity.
Yeah.
Okay.
Okay. So here, so we can write this expression as.
Even can you hear me? Yes.
Yeah.
Yeah. So what is the now? Let's say I have the effective Hamiltonian U, right? You have
Yes.
T naught T, and if I know the unitary operator, then I can calculate the effective Hamiltonian, Floquet Hamiltonian.
Yes.
So I'll ask you what you are going to do with the Floquet Hamiltonian. But before that, what is the motivation of doing this? U T2 minus T1. Why do you need this?
Oh,
You
okay.
in order to calculate this HF or
No. I am doing this to see that what is the general expression and what is the first motion operator, how it looks like.
Okay. So this T2 T1, those are smaller than the time period. So maybe
No. T2 minus T1 is very, very greater than T.
Oh, I see. Okay. I thought you were saying
No,
that
no,
those
no,
are
no.
smaller than that.
No.
Yeah, otherwise you cannot divide by.
Yeah.
Okay.
So that will be minus of IHF T naught into NT into UT T naught T1. And from here, if I write it in a full form, I am imposing some form. Okay, then the HF form. Then again I am writing this. Yeah, inverted.
Even can you go up a little bit?
Okay.
So which term you are sort of explicitly?
I am just adding one term, and then again one is multiplication and distribution.
Okay, then this term is there.
Yeah.
NT and whatever. Oh, okay. This term again you are.
I am just multiplying and dividing.
Dividing.
Yeah.
And whatever you still have U T naught T1, right?
Yeah.
Okay.
Okay, if I am not showing the full calculations here, from here, you can write this expression as p t2 t naught e to the power minus I hf t naught into t2 minus t1 into p dagger t1 t naught. You can write this expression in this form, where this expression is u t2 t naught into e to the power I hf t naught into t2 minus t naught. So what I am showing here, first I am showing that for any time period when we go from a general time t1 to a general time t2, then
Can you show it with some sketch that you are going from T1 to T2 this way?
yeah. Suppose this is a general time t1 and this is a general time t2, and suppose I am breaking, suppose I am my stroboscopic things is starting from here and this is ended from here. This is t1 star and this is t1 star plus t. This is one time period. But I am, especially what happens in experiment, because we cannot measure in a particular period, it may happen some error. So this is the evolution at initial and final. I am just writing this as P. Is it clear to everybody?
No, T1 to T1 star, you are saying.
Yes.
So your stroboscopic time is within T1 star, T1 plus. This is one time period.
Yeah.
But you can start at any time according to in your experiment. Can start at any time T1,
Yeah.
and it can end up any time T2.
Yes.
So how you are going to get to know that you know that T1 what is happening between T1 star and T1 plus,
And-
because that is known.
Yeah. But we don't know about T1 and T1 star.
Within this time, or T1 star plus T and T2, within this time you don't know. So
Yes.
you are sort of extrapolating, right? Once you know the stroboscopic dynamics within a particular time period, so
Yes.
you can extrapolate those things through this formula.
Yes.
Is it sort of meaning of that what you're trying to show?
Yeah.
Okay, so let me check. So e to the power IH, okay, can you go up a little bit? So your this is, you started with T2 and T1, right?
Yeah.
This is and then you know the dynamics within the stroboscope, but that I don't see here. Which one you know?
E to exponential of minus IH of it, this is.
So, okay, but go a little bit down here. In this, the last expression.
Yes.
I don't see that.
Mm.
In the last expression,
Yeah. From
I
here.
thought that the middle one is known, that e to the power I.
Yes. The middle one is known.
E to the power I minus H T naught
Yes, known.
T2 minus T1, okay.
This is known.
HF known, T2 minus T1, the time, okay.
Yeah.
And you are certain, okay, U T2 T naught, T2 T naught, HU. Okay, I understand. Okay, so yes, I understand. Now it's clear.
Okay. So is it clear for everybody?
Ivan, so
Yeah.
go up.
Yes.
I think if P is that, then in the first equal to line, the last two terms will be, first will be plus and the second will be minus exponential. To be the P and the last P is P dagger.
That should not be, because I have written it from some references.
Then what will be P1 P of T1 T0?
So what is the T2 T0? Just replace T2 by T1. You will get the answer.
Plus T2 by T1, then take dagger, then it
Then
will.
take dagger.
Then if I take dagger,
Yes.
there will be exponential and there will be a minus sign, right?
Yeah.
Okay. Okay.
Yeah.
Okay, sorry.
Are you fine?
Yes,
Okay.
yes.
Okay. So this the operator which take care of the evolution in the shorter terms, we call it the micromotion operator.
That means this P is a micromotion.
Yes,
operator.
yes. P is micromotion operator. And
Which is beyond the, let's say, which is beyond the, this operator is taking care of the motion happening outside the stroboscopic time scale.
yes, yes.
Okay.
This is called the out of the stroboscopic time scale called the micromotion operator, and this operator we can just give a representation of this operator, that is e to the power minus I. Suppose I am taking about P T2 T0. Okay, so for this I can write this as this kind of terms. This is also some kind of unitary evolution, and so I can write this in some kf kind of operator. This kf operator is called the kick operator.
Is it same? Let's say, can I write e to the power minus I kf t naught t2 equals to go to up equals to u t2 t naught e to the power I j?
Yes, in this total expression.
So you have two HF in general. No, overall. I'm trying to say that if t, let's say u t2 minus t naught.
Yes.
Yeah, this you can write in terms of also that Floquet effective Hamiltonian.
Yes.
Right, according to, then you have 2th, right? And then this 2h you can write, trying to say this is k.
Yeah. That is also dependent on the HF.
This 2hf at the same time t naught. Okay, go down a little bit, try to see. Okay, t2. So that's why I'm trying to understand how you can write this. What is the basis?
This is just as the P is kind of unitary evolution. So just I want to represent it in some form.
Okay.
This is just nothing more than that.
No, like I don't need to think about this this form of u t2 t naught t to the hf t naught t2 minus t naught, right?
Yes.
So once I write this, that means this p operator I can express this in terms of this.
Yes.
Similar to, because p is a unitary, because you are trying to take the same analogy you write from the Floquet theorem.
Yes.
For the unitary operator.
Yes.
Okay.
So, and one of the most interesting thing is that this micromotion operator is also periodic in nature. Suppose I can write it. You can write it as from the previous expression. Okay, I'm taking it T1 except T0. This will cancel out one each another. And we will again get back the previous expression.
So even like why these two are not getting cancelled, u1 exponential I t2 minus t1?
Which this? Because this is not the full time period, that's why.
Oh.
Because see, this in this u we have the time ordered part, no? Which may not commute with each other. Yeah, so how we will cancel? Unless and until you can write the total things in an effective form, how will you cancel?
Oh, okay. Oh, for that I need a total period. Okay.
Yeah.
Oh, okay.
Okay, so this implies, anybody, any questions? Okay. So this implies that the kick operator is also periodic in nature. And as this is periodic in nature, so we can tell that the dynamics within one period, that is invariant from the one period to the next one. Okay, and so I can tell that for any Hamiltonian ut2 t1, just writing this, we can write it as this is kind of evolution you can think of.
Like this is a generic, you are saying.
Generally, yes.
Before you wrote something, can you go back to the previous expression? So go back where you first wrote the Floquet, from Floquet theorem you wrote something, right? Okay, so go up, go down a little bit. Yes, this yes, this expression, the black one.
Yes.
This is a generic, right? U t naught t plus
yes.
IHT.
Yes.
But now you are trying to say, let's say if I start with any arbitrary time t1, we start with some arbitrary t2.
Right. Yes.
And it ends at some arbitrary t1, let's say.
Yes.
Or vice versa.
Yes.
So what will be the most generic expression for the Floquet, like if in terms of effective?
This is both kind of some effective forms.
Where you are basically, you don't need to think about what time you are going to start your dynamics. Is it just to remove this gauge T naught, like what time you are going to start, or something else? What is the motivation behind this?
No, this is the see, first of all, for any one period, suppose I am going from T1 to T1 plus T, then from here I am going to T2. For this case, we were able to find an effective Hamiltonian, but we were not able to write down an effective Hamiltonian for this part. Now I have just expressed this part as some kind of effective Hamiltonian.
Okay, so you are going T1 plus T and then T. I don't understand. Does it mean?
This is T2, sorry. This is T2. Okay. And this may even dependent on gauge.
This is a motivation. I understand. So you can, from the previous expression of whatever you wrote, you can write immediately if you know that T1 and T1 plus T. If something is happening within this time, you can write with e to the right HFT, right? And with the HF depends on T1. But you are going to not within the time period, beyond this time period, if you want to see the dynamics, then this is a more generic expression for that. Okay.
So what this expression of the evolution operator tells? This tells that from here we see that this expression mathematically separate out the show dynamics, which is governed by this HF, that is the show dynamics.
No, yeah, even there is one. Why there is a T naught here? Once you go, let's say, start with T1 and T2. Why
Yeah.
it at KF and or HF? There is no notion of T naught anymore, right?
So then this would not be T1, I think. Yeah.
This should be T1.
Yeah.
Right.
Yeah.
So what about KHK?
That will also be T1.
T1.
That's the effective things.
Mm-hmm. Okay.
Okay. So now my message is that we can mathematically separate out this slow dynamics, which is governed by the Floquet Hamiltonian, and we can also write some kind of the fast dynamics, which is governed by this kick operator.
How do you say that? Which one slow? Which one fast?
Yeah. I'm saying that by picture. Okay. So suppose I have a drive. And for this drive, this is my HF, and now this KF is a kind of this kind of motion. Where in this point the value should be same, but in other points that should not be.
Can you repeat? I didn't get to. This is the first is your motion, right?
Yeah. Actually, I can say that particularly for a Hamiltonian, we can calculate this HF is actually so dynamics in the sense that HF is static in nature.
Mm-hmm.
That's why we can write it as kind of so dynamics.
But KF is also static.
But actually thing is this takes care of the every mini event within one period.
Can you repeat again what you are saying?
The KF takes care of every mini event within one period.
Mm-hmm.
But the HF only take care about the full period.
Mm-hmm. Okay.
That's why in that sense KF HF, the staticness of the HF is much more than KF.
Okay, I understand. Now you are saying that so HF is let's say it's a long wavelength kind of behavior. And where KF is a very short wavelength physics.
Compared to HF.
Yeah, compared to HF.
Yeah. Okay.
Like it's sort of it's looking that if you think about phononic system, like you have an acoustic phonon which is a long wavelength, but optical phonon you get to know the motion of each unit cell. So that is the long wavelength behavior is sort of slow dynamics, and short wavelength behavior is a fast dynamics.
Yeah. This dynamics is much more accurate in a high frequency regime. Then the KF will be much more exact.
Okay. But yes, the picture actually doesn't show say anything. Like you are saying by picture, but there must be some underlying reason, like why they are drawing this picture. Whatever you were saying is. I sort of agree that yes, HF is the full wavelength behavior, like with taking care of everything within the full period of the system, but KF is taking only the small part of the system.
Yes.
And in terms of, I can say that this is a
but at periodic point this would be same. Yeah.
Okay. Go ahead.
So now I will discuss a little bit about the quasi energy.
Ivan,
Yes.
Why this is short period? Can you explain again?
This is within one period. No?
The KF is very rapidly changing, right?
Yeah, that's why it is called the first operator, kick operator, which is first motion.
Okay.
Yeah.
Okay.
Now I will talk about the quasi energy and Floquet states. So to start this, the thing which we have told first time, we are still now keeping this. Sometimes I may miss the T0 part. Okay. So see what this says. This says that as the operator is unitary in nature, that means that its eigenvalues are complex number which rise on some unit circles. Okay, and you can think of that each kind of this kind of forms. And as this is the unit circle, so obviously the omega there is the in the energy there is COD some modulus of 2 pi. Okay, so suppose that for this HF, the eigenstate of this HF is N. I am thinking. Okay, now suppose I have an initial state which is psi t1, and I am expanding this psi t1 in the basis of the HF. Okay. Now I have another state psi t2 which I can get by the evolution operator on psi t1. So what I can write? This I have already written previously.
Just to even, can you again repeat this unit cell? Probably it's not clear to all of others. Like you have gone through why you are taking complex plane, you are considering everything. Can you explicitly, a bit elaborately, like?
This is some kind of the.
So you is a unitary operator, right?
Yes, yes.
So you're trying to get to know the eigenvalues of the unitary operator, right?
Yes, yes. That will be this kind of forms.
Yes.
And this is
No,
just.
are you sure? No. Eigenvalues of unitary operator will be eigenvalues. Okay, this kind of form.
Yes, yes.
That is imaginary.
Yes, yes. With magnitude 1.
Yes.
So that will lie in some unit circle in complex
unit
plane.
circle of a complex
plane.
Okay.
Yes. Yeah.
Okay.
Okay.
Go ahead.
So now I am trying to find what is psi t2, which is after some evolution from t1 to t2, and I am using the previous expression. Okay, this is the form of u I have written previously, and this is the psi t1. Okay, so from here this HF's eigenstate is N, so I can keep it out. That means, sorry, I am writing this as UNT2. Just I am representing this. And this is the Floquet modes. We call this as Floquet modes. And this is periodic in nature. You can check. Because the KF is periodic in nature, so this is also periodic in nature. because n is time independent. That means un t2 plus t equals to un t2.
Even can you go a little bit up? Okay, psi t2 you are saying. T2 minus T1. Okay. Yes.
Okay. Okay, so what about the psi t2? Psi t2 is e to the power minus I n t2 minus t1 into un t2. So, and this is periodic in nature. Now, can you compare this with what we have got in Bloch theorem? This is the e to the power minus
Sum over n, right? You have sum over n.
Yeah.
And Cn.
Yes. Sorry. So this is kind of things what we get especially in Bloch theorem, and this Hamiltonian is called the Floquet states. This state is called the Floquet state. Sorry.
Difference between Floquet modes and Floquet states?
Floquet mode is just the UN part. We define it as, and
which is the, you are saying the periodic part of this?
Is called the Floquet modes.
Okay. And Floquet state like a block state.
Yeah.
Okay.
So HF gives us the opportunity to treat this problem as if the time independent. Okay, and at the stroboscopic times, this description is very exact in nature, and but when we take care about the Floquet modes, this is on the main attention of our main topic, which we want to take care when we take about the non-stroboscopic time. Then we need to take care about the event not much more. Otherwise, if in stroboscopic case, as it is periodic in nature, we don't think too much about that. And also, just for some remarks, that though this Bloch theorem and Floquet theorem is a little bit similar, but yeah, there are some differences also. Because first of all, the Bloch theory is actually a spatially periodic but temporarily static problem. But Floquet theory is a time, this is completely on time. That is one of the difference. Okay. Otherwise, everything, the concept is very similar. Though Floquet has developed it much more before than Bloch. Okay. Now, I am going to the thing which I was trying previously, stroboscopic.
But there is another crucial difference. Like in the case of Floquet, you have the spatially, like let's say you are trying to solve the Hamiltonian Schrodinger equation, even for the block, right? So your kinetic term has a derivative, second derivative.
Yes.
Right.
Yeah,
but you don't have this structure here. Here you have time derivative, single time derivative in there.
Yeah, you can think of that for the Bloch case. We try to reduce an infinite dimensional Hamiltonian to infinite dimension kind of things. But that is not in Floquet. Yeah. Okay, so now I am going to stroboscopic and non-stroboscopic things.
So just you told several times stroboscopic and non-stroboscopic. I don't know if everyone understand what is
Yeah,
stroboscopic. Just to give you,
yes.
others may know from classical mechanics, but I don't think everyone remembers it.
Yeah. Let me just see the picture. Yeah, stroboscopic means we always take care about one or multiple periods, but for the non-stroboscopic case, it is something more than a period. Especially what happens in experiment, we cannot measure every time in proper periods. That's why this is also important things experimental. Okay. So
Yeah, so even that means for experimental to be more close to experiment,
yeah,
we need this UT to, because you told that for
Yeah.
stroboscopic we don't need to think about periodicity of UT2 or this form, particular form, but
yes.
for the non-stroboscopic modes and everything, right?
Yeah.
To make it very close to the experiment. Okay.
Yes. Okay. So now I want to take one thing that what we have was talking that HF is dependent on T naught. Okay. But now say I cannot, I may not start from this. I can start from this. I can start from this. I can start from this. And if every time I count for one period, our expression should be same. That means that one can choose a family of stroboscopic Floquet Hamiltonians HF T naughts for any evaluation things, and each one exactly describes the evolution operator at stroboscopic times. And this choice of T naught is called the Floquet gauge choice. And main things is that different stroboscopic HF are gauge equivalent. That means if I know one HF at any T naught, we can go to other T naught by just some kind of using the micromotion operator. Okay. And now there are also one important things. When we talk about a total family of HF T naught, so there should be, even always be, some kind of Hamiltonian which don't take care of T naught. That means this is not dependent on any initial choice. That should be. Because suppose think of that we have an electric field, and suppose a particle is an electric field. That means this kind of form in the Hamiltonian, the dependence of in this E, we can keep it one form, or we can also keep it in this form into T. See. So what this means, so if we give this phi and not this, I am trying to eliminate this. Suppose I am a minus of grad phi. Okay, so this is, and you get one E from this expression. That means there is no T dependence. Okay, now if I set some gauge in the A and there are some dependence of T, and after the derivative this go away and you can get back the same E. That means in the case of phi there was no T dependence. In the same way, here for the family of the total Floquet Hamiltonian, there should be any one of the Hamiltonian which don't depend on the initial choice. That is called the HF. And you can write this HF. This HF is also gauge equivalent. Okay. So
Even K is this micromotion operator, is a different
yes,
operator.
this is the kick operator.
Keep
The total
operator.
things is micromotion operator. Yeah.
So better put KF because you probably put KF
Okay.
before.
Okay.
So you are saying that you can, with this micromotion operator, you can make it initial gauge invariant.
Yes.
So essentially writing this HF
Yeah.
without T naught, that means you are sort of making this gauge invariant, right?
Yeah.
It doesn't depend on the time you
Initial
are starting.
time, yeah.
What initial time? Okay.
Yes. And this is actually much more important if we when we want to sum spectral properties of the material, like the transmittance or absorbance. Then we don't like any kind of the Hamiltonian or other things which is time dependent.
Yeah.
And for this case, we actually, this is more favorable to find an HF kind of things, which is not time dependent. Okay. So this kick operator and the
It's not right to say time dependent. Better it doesn't depend on the initial time.
initial time dependent.
Not otherwise.
Yeah.
Full time dependence.
Yeah. See. Sorry. Okay. So this kick operator and the fixed HF. Okay. From now we will take this as this is called the stroboscopic HF. And this is the non-stroboscopic HF kind of things. Then it is better. We can also write this as fixed HF. So this kick operator and HF, they are also not completely independent. And from this expression, we can see that there is a particular choice of HF, which also we can write as the H effective. That will be much more easier. And this operator now, so as I am telling that now our Hamiltonian, there is no time dependence of initial time dependence. Okay, so that means we can also find an K which is also not initial time dependent.
Didn't get what you are saying. For initial time.
That means H effective, which is not independent of HF T naught, and I will also get an K effective which not equals to KF T naught.
Okay.
Both will be initial time independent. You can find that.
Okay. You are going to show it,
Mm,
or it says some argument.
yeah. No. I will discuss about this in some application. Yeah. See.
Okay.
Okay. So yes. One kind of things I can show from here about the relation between this kick operator and the first motion operator, that is this operator, how they are related. Okay. I can prove it. Just suppose I am talking about a Hamiltonian in this form. Okay, just I am deviating from T naught to some point. That means we can write it as Yes. Okay. Now I can write this as some kind of the effective form. And also I can write this as this implies I am taking it as T and C. Yeah. This is the kind of term we can get.
I see. Okay.
Okay. So now we can write it as I am just replacing the p's with this. And we can write this part by the effective Hamiltonian. There is no T dependence. First there was the choice of gauge, but here there is no choice of gauge. Okay. So this kick operator also describes the dynamics of the system within one driving period. Okay. So now I want to see this in some application that is called what I am telling till now. Two-level system in a circularly driven magnetic field. Okay, so here the circular motion is perpendicular to the, this is in parallel to xy plane, and we can write this as this is our Hamiltonian. And so this is dependent on time, where along this z-axis this is moving. And now how we can, yeah,
no, it's a parallel direction is moving, right? XY plane is moving.
yes, axis is z.
Oh, along, okay.
Yeah. Okay, so how we can solve this problem? I am not going to solve it in exact way because that is very common, but how I can solve this problem by changing the frame. So what we can from this problem, our main aim is how to find the evolution operator. Okay, this is our main interesting things here. We want to find it. Okay, so what we can do? We can do first we want to go to the rotating frame. After that, find the simple evolution operator, and then
So
again,
if we go to the rotating frame, are we going to make it static Hamiltonian?
yeah, that should be time independent.
Oh, I see.
But
So then you don't need to solve the Hamiltonian, right? You don't need to find the unitary or Floquet. You don't need to do. If you go to the rotating frame,
yes,
if it becomes a Hamiltonian, becomes completely time independent.
yes, but
Then do you need to use Floquet theory then?
but what about the lab frame? I just want to compare both things.
Okay.
Okay, so first we will go to rotating frame, then for this frame we will find the U.
So Ivan,
Yeah.
This rotation you mean that by this rotation the Hamiltonian will become time independent because of that thing?
Yeah. But there is also an interesting things that from which time I am starting to shift my frame to rotating frame, the evolution may be dependent on the T dot. Yeah.
Okay. Yeah, that is okay. So so that means that your rotation frame is not unique.
No, yeah, surely not. There is a family of the frames, but surely there should be something that is time independent. That is a gauge equivalent effective things.
Okay.
And I will try to show two things.
Okay. Let me see.
Okay. Yeah. So first of all, I am just suppose that what is the for any spin. Okay. So how we can rotate it? What's the form? This is the kind of form r theta, that is exponential of minus I by h cut into theta dot L. That is the general r theta for any spin, where L is the angular momentum. So here, if we try to rotate for this case, then I am transforming this operator as
So you are trying to. This is your rotating operator.
yes. Transform rotating frame to lab frame.
So which means that you are going from time independent to time dependent, right?
Yes. This is the rotation operator.
What is this omega?
This omega is the frequency of the movement of the rotation.
Okay.
But can you show how you can make it time independent in the rotating frame?
Yeah. I will show that.
Because you are
Yeah.
now operator you are writing, it can take you from time independent to time dependent.
Yes. I am going to show that. Yeah.
But first you told you want to go to rotating frame. Then I want to see that what is the effective Hamilton if you go to the rotating frame.
Yes. I will.
And how they are connected.
Yeah. So this transforms from the rotating frame to the lab frame. That means first I need to go from lab frame to rotating frame. Then here I need to search for this HF rotation, and then I again returning from rotating frame to lab frame. Okay. So Now, first of all, this is our interest. What is the H rotation? This we can write it as,
One moment. So you first V dagger, that was T1, T0, and it is T2, T0. That is the time order or it is the same?
this is the time. From which time I am shifting from left to rotating frame.
No. You wrote T1, T0 and T2, T0.
First is this last is T0 to T2.
Okay.
And this is the T1 to T0. Means this there is a dagger.
Okay. So it's in interaction picture, right? Or
yeah, you can.
No, I don't think this is interaction picture, right? You are trying to.
no, I have no. Actually, this T2 and T1, that order I am not getting correct. T2 and T1. So at time T1, you are actually in the rotating frame, and then you are trying to see the particular.
Okay. Then I can. This is I can T0. I can start. Then I think much more fine. From T1 to I am going to T star, and then from T star I am going to T2.
Okay, and
Oh, it's because of dagger. You have this.
Yeah, T star and T1 actually changed the position. Okay. So first my interest is to find the H rotation.
That means whatever the Hamiltonian in the lap frame, you want to get it to it at the rotating frame, right?
Yes. Yeah.
Which you will make the Hamiltonian time independent.
Yes. So just one thing I want to tell that suppose I have a side dagger T and I am giving some kind of evolution to this, which this is kind of the V kind of forms. Okay, much more better if we write it as V. So IH cut del T of psi T, that will be IH cut del V del T into psi dagger T del T psi dagger T. That means this is the H psi T IH cut V dot psi dagger plus IH cut V into del T of psi dagger T. Okay, now I am just replacing this psi T as V psi is replacing T. Okay, so H and this IH cut del T of psi T equals to in the rotated frame or in the transformed frame, this is the psi dagger. So plus H T V I V T V dagger V. I think up to this is fine, right? So this is our rotated Hamiltonian now. Now think of this V as our rotation operator. Okay. So H rotation T0 equals to V dagger T T naught H T V T T naught minus I V dagger T T naught V dot T T naught. We know this H from previous, we know the V, and we can do the total calculations. Okay, I am just writing the answer because this is too big. This will be yeah. See, this is also dependent on the gauge T naught from in which time we started. That is T start was. Okay. And
Yeah, you keep it to T naught because it's okay. Unless, because you wrote omega T naught, right?
yeah.
So, but you get additional term.
Yes.
Just because of this rotation.
Yeah, this see there are also a huge change because in HT there was the T dependence, but here it is T naught dependence. Though it seems very natural, but this is actually very huge calculations here. This is actually 2-3 pages. And from here, if we try to find the eigenvalue of this rotation, that will be okay, that will be this. And now think of that this is the energy in the rotating frame, and now think of that we are rotating the magnetic field in a very high frequency, that means omega tends to infinity. So the main problem here, that see, if this is infinity, the E rotation also will tend to infinity. That should not be the case. And so but what we can expect from our Hamiltonian, see, if the Hamiltonian is this Hamiltonian, if the magnetic field is rotated too much, we can cancel out the dependence of this term, and from here, if we just take the time average of the total part, I can think of this in this way. That will be just Bz sigma z will be left out. That should be effectively.
Yeah, that means omega is very large. Average of cosine and sine t would be 0.
Yeah.
Right,
and only Bz sigma z will be left over. Yeah.
But it turns out from this in the rotating frame, this is not the case.
Yeah. Okay. So there are some problems. Now, how to fix this issue?
But in such cases that that's a rotating frame, what will be the frequency of that rotating frame?
Frequency will be the same as the how the magnetic field is rotating. That is.
They're so fast then.
Yes. Otherwise we cannot go to in any static frame, no? If we don't do that, then again there will be time dependence. So what?
So it means that you can actually you try to conclude that by that much frequency I can get time independent, or vice versa, right?
Yes.
Wow. Okay.
Okay.
Yeah, because your time rotating operator, like this V, which actually depends on omega, right? The same omega.
Yes.
The frequency of the effective your starting Hamiltonian.
Yes. Okay. So first of all, I need to find out that how to fix this issue, and from here, one thing we can say that I just think about this, that if this is the case, this is the T naught plus 2T T naught. Sorry, why I written 2T? Okay, that's not matter. It may be T. 2T. And see, for this case or this case, okay, so for any total time period, as we are talking about only time periods, so that means this HF T naught and H rotation T naught, they should share the same eigenstates. Okay, otherwise they should not be in the same unitary evolution operator in a time period. But our problem is to kick out these 5/2 terms, because this is the main point. And yeah, if the eigenstate is same, but the eigenvalue can differ by a shift of plus minus omega by 2, that does not matter. Okay. So we can fix this by using these terms. And suppose I am writing it as minus term. And suppose S is a unitary matrix. That means that S into H rotation T naught into S dagger should be epsilon rotation into sigma z, kind of things. Okay, so what about the HF T naught, Floquet Hamiltonian? Okay.
So just you are trying to say you want to get it back, like in the high frequency, in your static Hamiltonian, the time dependent Hamiltonian should give you some time averaged Hamiltonian, right? And
yes.
Get to the corresponding eigenvalues, which is BZ.
Yes.
Right? Plus minus BZ.
Yeah.
But it turns out in this particular case, if you go to the rotating frame, and if you think that okay, omega is infinity, then your rotation goes to infinity.
Energy diverges.
Energy of that frame in that frame goes to infinity.
Yes.
Now, in order to sort of make this E rotation finite, right?
This is kind of intuitive guess.
I see. So that is not clear to me why you are trying to connect this unitary operator with Floquet, and you know that okay, time dependent case, I write according to Floquet theorem, I can write it.
Because still now HF have not came in the picture. Now I am just illustrating this.
So let me get from you some clarification. So HF is not in the picture.
Yes.
But you know that from the Floquet theorem, you have unitary operator, you can write it as effective e to the H shape T naught, right?
Yes.
You can write.
Yes.
But for this particular Hamiltonian, you are trying to compare the same unitary operator with HF H rotation. That is not clear why. What is the... Why you are trying to compare this?
No, this is, I am trying to compare this because first of all, here I am comparing only in one period, not for any general evolution.
Yes.
So that means whatever frame this will be, is in one period that should be same.
H rotation and...
Yes.
in one period it should be same. You are saying that.
Periodically, that should be same.
What is same? I don't get it. What is same there?
The evolution operator, U T naught plus T naught.
So you mean that within that this thing that this evolution operator will be independent of any rotation, or what is?
No, I see. Probably you didn't miss that unitary operator according to Floquet theorem, if you have a time dependent and Hamiltonian, so
Yes.
you can write unitary operator in terms of some HF, which
Yes.
is some Hamiltonian and some capital T, let's say some period. Okay?
Yes.
That you can write according to Floquet theorem.
Yeah.
Now you are saying that I have a problem which is time dependent.
Yes.
Now somehow I write it, I go to a different frame where I get some effective Hamiltonian which is time independent. So definitely from the same expression of Floquet HF is sort of time independent. So you can also write it must be equal to exponential of minus I H rotation, which is your effective Hamilton times capital T, right? This
Yes,
is the
yes.
according to Floquet, this is the case, the left hand side equal to U. But since I am also dealing with some Hamiltonian which is time dependent, and I go to a different frame where it becomes time independent, so I can sort of connect this must be this rotation must be connected to HF. That may be
Okay.
a result to compare.
And they share same eigenstates, but may not be the eigenvalue be same.
Okay.
Okay, they should, because same eigenstate. Why you are saying they should share the same eigenstate?
Because this H effective the things what we have written, okay, that should commute. If they commute, then there should be same eigenstate.
Okay. Okay, I understand. Okay.
Okay. So, but eigenvalue may not be same, and that's why we try to fix the omega by 2 issues here. And this is kind of intuitive things that we can check by plus minus omega by 2 in rotational frame, rotational energy.
To make it more sensible to the...
Yes. Because I need to get out from that. Okay. So that's why I have written the Floquet Hamiltonian. This is kind of intuitive. I will show it in later day. The same expression comes from the Magnus expansion or the effective theory expansion. But this is kind of intuitive things how we get that. Okay. So
with this you are trying to say that you will not have infinite energy. You will have finite energy.
I am in a finite energy. Yeah.
But let's say you add the energy rotation, this omega by 2 is square, comes with square, right?
Yes.
Inside the square root.
Yes.
So...
No, actually, if this is very large, you can just neglect omega by BZ. This kind of things.
I see. Okay.
This kind of things.
Okay.
This is the high frequency, completely high frequency things. Okay. So now we know the HFT naught, and now we need to know the PTT naught. This is one of the most important things, because if we know that, then I can totally write the total evolution operator. Okay. So V2 T2 T naught U. Now this is the previous expression. This is our new expression of unitary evolution operator U. Now by comparing this, I am not doing the full calculation, but by comparing these two, we can get P T T naught equals to exponential of minus I sigma z by 2 omega T T naught Okay, and now I see that this is composition of the two rotation operator in spin space. So whatever we have got till now, P T T naught, H F T naught, H rotation T naught, and E rotation T naught. These four things are known to me. And also other one things I want to mention, because this P is also periodic in nature, one can check, and also P T naught plus M T T naught should be 1, which we assumed before. We can verify from here. Okay. So now this is one gauge, but see, in this gauge also there is some kind of T naught dependence. So this is also some kind of there is also the gauge, there is also in gauge which is T naught. But now I want to get rid of this gauge and try to see the different choice which I was writing, and that's why now I am writing the plus omega by 2 term. Okay. So,
how did you get this? Sorry.
Yes, there are two choices of me.
Okay.
I have just used one choice, and that gave me the again one form which is dependent on T naught. Now I am trying the second choice.
So why you are taking minus C rotation?
Because now I am just if you change the sign here, omega by 2 first, BZ, because this is square, that does not appear.
Yeah. Oh, I see. You rotation, you have 2 plus minus, right?
Yeah. And from here, if we calculate the UT to T1, like this kind of things, e to the power minus I k effective T2, e to the power minus I h f T2 T1 to the power I k effective T1. If we calculate this, we get the k effective T. I am not showing the full calculation. This is very complicated. That will be this. See, and the most interesting thing is here there is no T naught choice. That is the most interesting thing. Where alpha is okay. So now just think that in the high frequency limit where this omega very greater than Bz, that means here what is alpha? Alpha tends to pi, because we can think that sine alpha equals to B parallel by E rotation, and from here just cos alpha equals to dz minus omega by 2 by e rotation. And just if we think about that this omega is very large, then there will be omega on the minus 1, and so alpha tends to pi, and this assumes that b parallel is also 0. This is the high frequency case. So this is just the, I am saying what
But you say in the high frequency K effective turns out to be 0? Because alpha becomes pi.
Yes, that was expected, because b parallel should be 0 in high frequency case.
No, K effective. It seems if you go to the very high frequency, then K effective turns out to be 0, alpha equals to. Because sine, you take an average of sine and cosine.
Let's see, cos alpha will be, but how we can tell that?
No, K effective is alpha minus pi by 2.
Yes.
Times
Okay. Yeah.
Alpha equals to pi.
Yeah.
This
Okay.
your K effective is 0. What does that
Yes.
it tells? What is the meaning of that? K effective 0?
K effective should not be 0 first of all.
But your calculation is showing 0,
Yeah,
right?
because if anyway it is 0, then there will be disaster. Okay, let me see. Because then if every K will be 0, that should not be the case.
But at least at the high frequency,
Yes.
0.
Yes, I don't know that somehow.
Or you have something wrong in your expression.
No, because this expression is completely checked. The final answer is checked. That's why I'm trying to think. Probably I'm missing some interpretation.
Yeah, some issue is there.
Yes. Calculation is not wrong. Calculation is completely fine because I'm checked. Okay, I can see it later.
Yeah, you can check later.
Okay. So, whatever we have done till now, and also one thing I mentioned from here, that if you look at this expression, at any t, that should not be completely vanish. And that's why this is the non-stop, and this is the property of non-stroboscopic kick operator, because in case of, suppose in choice of gauge, in G0, there may be some time then it completely vanishes, and I have seen that. But that should not be the case in non-stroboscopic case, because there are some extra evaluation in the period. Okay. So up to now I am written everything in. Now I want to interested in see the dynamics of these things. This is the last part. Probably I will end here. And so what we mainly interested in dynamics. First of all, I want to show that the two things we have already done, hf t2 minus t1 e to the power I kt1, this is the effective things, and the other thing is t2 Now, first of all, in dynamics, I want to see the expectation value of observable. This is the first thing I want to know by using these dynamics. Okay, so consider some observable OT2. This is just time I am thinking. OT2 is a time after T1, where T1 is the initial time. And I want to see it in the Heisenberg picture. Here the assumption is that in initial T1, I have mentioned the state in some fixed pure state and written some density matrix rho for that. Okay. So now if we average it OT2, what will this be? This will be rho U dagger T2 T1 rho U T2 T1. Okay, so if I explicitly write this, this will be okay. This is the full expression. I am just jumped some steps. If you put everything U and U in the explicit form from here, you will get this expression. Okay, so first of all, I want to mention some things. See, now I am writing this as rho effective. I am writing this as O effective. Okay, and I want to mention something here. First of all, these KT1 and KT2, which is written here, that can be viewed as the time dependent gauge transformation, what I am seeing. And but here this rho and A are transformed, and just think of that I am thinking that T1 and T2 are independent to each other. Okay, initial and final time are not dependent, because that is the common scenario in experimental setup in maximum case. And for this case, so the evolution of rho and O, they transform completely differently until T1, T2 minus T1 equals to NT. If this is the case, that is different things, very special, but that may not happen. But in general, this T1 and T2 is independent to each other. And when this happens, we surely talk about some stroboscopic things, but that may not be the case. And at this case, the KF T0 may vanish at some points, but the rho and O maybe in one period they remain same, but that is not the case from the non-stroboscopic things. In non-stroboscopic things, the rho changes to rho bar and O changes to rho bar according to our assumptions, and these are called rest operator. There is also some evolution on rho and O. Okay, so
in order to calculate dynamics, then you have
yes.
to know K and HF, right?
Yes, both.
Or you can do it unitary. Or now you don't know rho.
Yeah, I know the initial state, and from here I can construct the rho.
I see. Okay.
Okay, so and this is what I can tell, this rho bar equals to, so what we can do now for our calculation on some theoretical purpose, I can take this rho bar equals to, just think of e to the power I k t1 into rho e to the power minus I kt1 and take average over this period to get some effective rho in our calculation. We can do that. Similar case for O bar. Okay, and if you think that this, if I do this, so two things I want to mention here. First of all, this T1, T2, there are some assumption, and T, that is T2 minus T1, that are statistically independent variables. This is our assumption, but in reality that may not be every time. However, if this T is very greater than del T1 or del T2, which are the cases in this side and this side, if this T difference is much more greater than that, then we can consider that this is also independent with T1 and T2. This is effective independence. Okay, now in high frequency limit, we have learned two things. This is the fast dynamics, this is the slow dynamics. And now if you want to average over T1 and T2, which I want to do here for this case, now provided that this T, del T1, del T2, they are independent in nature, we can assume that this expression e to the power minus IHF T2 minus T1, this expression is unchanged, because this is very static rather than them. This is our assumption. So this averaging procedure, what we are trying to show here, this will affect only this and this, not this part or this part. So that means, so this rho bar actually now we are, after averaging, this rho bar is not dependent on the initial driving phase, right? Because what we have written as rho, now after coming to rho bar, there is no dependence on the initial driving phase, because now it is averaged over the full cycle, and that is the same things for this O. So even we start even if we start from any pure rho, okay, if we start from any pure rho, so and if we go to rho bar, so we can think of that now we are going to a mixed state. This is what we can think of, that this averaging procedure over the full cycle that actually broadens the full density from initial density matrix. And the same things, that this is played by temperature on that. So this is kind of some analogy. Okay. So other one things I want to mention, that one can check that this not equals to this, and in high frequency limit, Dressed operator satisfy Heisenberg equation of motion. These two things anybody can check.
Yeah, so even so, do you have any example like how to calculate actually in real problem?
Yes.
The K
Yes.
and
I will end by showing that. Yeah.
Even another problem I think is that what kind of experiment do you mean?
Experiment. Are you talking about experiment?
Yeah.
Suppose you are driving. Suppose you are driving something by right, and now just see what is the refractive index or other things. How changes. Now how will you see that? You need to find the H effective.
Okay.
Yeah, anyone, can you come finish it in 5 minutes?
Yeah. 5 minutes. Yeah, surely. Yeah.
But you can't do Magnus expansion, all these
No.
things.
Today I cannot do.
Yeah, okay.
Yeah. Today I will just see the gauge equivalence. Yeah. So now if the case which I have written here, for the first case where I got the HF T naught and the other things, okay, HF T naught, rho T naught, in the stroboscopic case, in the two-level system, if we calculate this, the sigmas, where the HF naught equals to 1 minus omega by 2 E rotation into H rotation. Okay. For this case, if we find this, one can use the Baker-Campbell-Hansdorff or some just using it matrix and then averaging out. You will get this as sine square alpha by 2 sigma y sigma x f bar sigma x sine alpha sine square alpha by 2 sigma z and sigma.
No, I understand. So you have some expression. Can you explicitly tell how you are going to calculate e to the power I f0, kf0? What is kf? What is kf?
This kf is what I have calculated here. Okay, let me show. Yes, this kf.
Oh, okay. Oh, so you write effective. That's why it's sort of.
There are two things, each effective or one other kf. Okay.
So kf is same as the k effective, right?
This is k effective. And from the previous things here, anyone can find the other one, e to the minus k. This can be just calculation. One can do that.
Okay. Oh, okay. I see. Okay.
Now one can use the Baker-Campbell-Hansdorff for other things and just
then it's easy to calculate. Once you know that it to the kf, then it's
yes.
to
Yeah.
That's the main important thing. You have to know the kf and also hf.
Yes. That two things we need to determine everywhere.
Yeah.
Okay. So just one thing I want to mention, that again in the high frequency limit, you can check that the alpha, here also the omega, this alpha, I have told that this will be equivalent to pi, and if you put that, then again this will reduce to sigma y, sigma x, sigma z. Because cos pi equals to -1 and -1, this will be 0. Okay. So this is one thing. And now do the same calculations for the effective case in the same way. And we get, just I want to mention one thing, this is important. This is the calculation by calculating in the whole things in the non-stroboscopic scenario where there is no time independence. This is the stroboscopic case, this is the non-stroboscopic case. And here also if you take alpha tends to pi, they again go to sigma x, sigma y, sigma z. So all the observables are giving the same things. Okay, this is in high frequency limit. And also one thing that I mainly want to mention, that see the scenario in stroboscopic case and non-stroboscopic case about the sigmas. And you can see that unlike the stroboscopic picture, effective Hamiltonian picture preserves the rotational symmetry about z-axis. This is the case, and one of the main important thing here.
Let's see.
And that is kind of things one can tell. This is kind of the difference between the Landau gauge and symmetric gauge for a particle present in a magnetic field. This is the same thing, that kind of intuition applies here. Okay. And this effective gauge, you can think of that this effective gauge is more convenient in maximum cases, but especially if we want to see the spin dynamics in some kind of reference, for that cases we need to use some kind of Landau gauge things also. And also one things one can verify that this drift operator not equals to 2i sigma k. And also the mixed state things. Okay. These two things also the property of the drift operator.
So this even so this theory can be applicable is applicable for light driven any magnetic phenomena.
Yes, this is you can apply it any Dirac class of systems or Floquet topological insulators, some kind of spin flipping systems.
Yeah, yesterday there was a talk. Actually, I had this talk. It's a quantum magnet. They have done something, a highly interacting system and driven like quantum magnet. Recently, they are doing this in octagon system. What is this system? Ruthenium chloride, RuCl3.
Oh, that is actually AC J equal to half system, right?
Yeah, right. Half the J equals to half system. You have Hund's coupling and all sorts of charge ordering for ruthenium. This is a special system. They are doing this Floquet. Although the guy who was doing this, he was not very familiar with the details of the Floquet. But people are doing on this applying Floquet perturbation theory. And there is one interesting question was the stability for stability, and if you are driving the system, then are you really staying in the ground state or you are going completely out of the ground state? Those are some interesting questions still exist for this quantum magnets and all this. So, but the essential method that you can use theory for quantum systems.
So this basically there will be a quantum magnetic J. There is a transition in the magnetic state. Actually.
Yeah, they have the right all sorts of transition they are going to see.
Interesting. Okay.
So even next time, I don't know if further.
Yeah, not in next week. Next week, Subhajyoti I give the talk, and then again I will come back.
But Ivan, I think this next time maybe you just connect this with some real problem.
Yes. Next day I will. Yeah.
And also that how people do those things. Maybe approach people do those tackle the problem.
Okay.
Then I think we'll get some idea.
Yeah. Okay.
So.
Okay. Another announcement I want to so recently last week I met some experimentalists in cultivation. So maybe next month or next end of next month. So this experiment they want to give a talk on. I don't know whether you people heard the talk yesterday by Sunil Mukhi. So there people are talking about this axion thing, and in cultivation people are doing experiment on the same system. So maybe it is a good time to look in that direction, and if someone want to do this thing, so they want to collaborate with us. So let's see. Okay. So maybe after 2-3 weeks they will give a talk here.
Okay, good. Yes.
Okay.
Any question from the student side?
I am very surprised that students are so either they don't understand anything or they understand everything.
No, I guess the interest.
I don't know. What is this, man?
The kind of things, maybe I don't know.
the interest because okay. Okay.
Anyway, let's here next talk. Who is Shubhadeep is going to give it?
Shubhajyoti. Yeah.
Subhajyoti. Subhadip will give maybe after 2-3.
I see. Okay.
Okay.
So then
Chalo,
you can
bye.